Okay, so guys, welcome to the lesson on the life cycle of stars, and I think this is a great lesson. It also talks, I'm also going to talk to you about the origin of our solar system, so it's kind of a really cool story. It's about where everything you see around you, ultimately, where does that come from? Okay, how was it brought into existence in the first place? Okay, so let's get right to it. Where do solar systems and stars, how do they form? Okay, so I made these notes for you. I don't want to just read them. I'm going to show you some pictures as we go along. Okay, but anyway, our solar system, we think what happened is our solar system was formed when a much larger star exploded, and that's called a supernova. We'll talk about that later, over 5 billion years ago. And when the dust settled, our solar system was born of that dust. Okay, so what am I talking about? Well, what happens when you have dust in space, dust and gas, is gravity pulls it together. Okay, and under the force of gravity, you can get a larger and larger ball of gas forming. Okay, and around that ball of gas, because it has so much gravity, it'll start collecting things in a wider sort of area of space, and you get like what looks like a disk forming called an accretion disk. Okay, now when gravity gets strong enough at the core of the star, the temperature can increase, and once it gets to 15 million degrees Celsius, and we talked about that number before, if you can get to 15 million degrees Celsius, nuclear fusion will start, and now you have a genuine star. Okay, now the remaining material that is in the accretion disk can form planets. Okay, so that's the deal. Like, that's basically where our solar system came from. Now we see this happening when you look through telescopes. We see this happening elsewhere. Okay, so I'm going to show you some pictures and so on, but like, just let me review this like sort of in point form. So number one, another star exploded, a very massive star, much more massive than our sun. It could be maybe 20, 30 solar masses, something like that, over 5 billion years ago. And that formed what we call a nebula, which is basically a big dust cloud in space. Okay, it's pulled together by gravity. So I mentioned that here. Okay, so 5 billion years ago, another star exploded. It was pulled together by gravity. Okay, now when things pull together, like the figure skater, they tend to start to rotate. Okay, and so what happens is you get this big ball of rotating gas, and then as the ball gets bigger and bigger and bigger, there's more and more gravity, more things get pulled in. Okay, and they join the party here. Okay, and they're going to start forming like a sort of a collection around that big ball, and that collection is called an accretion disk. Okay, now once it starts getting really hot because of gravity, like if you squeeze atoms together, they're going to start heating up. Okay, and the ball will start to glow because it's hot, and hot objects do glow. Like I said, a red hot object glows red at certain temperatures, right? It'll go blue at higher temperatures, and so on. So the little ball of gas is not a star yet, but it starts to glow. At this stage, we call them protostars. Proto means before. Okay, so before it's a star, it's a protostar. It's not officially a star yet, even though it's glowing. It has some brightness; it can be detected. It's still not officially a star. Okay. Now, once 15 million degrees is reached in the nucleus, so if the ball of gas is big enough, if it hits 15 million degrees Celsius, you're going to get nuclear fusion. And that is key. So the hydrogen atoms will start, they're squeezed so hard by gravity, they're going to fuse together and form helium, and then a tremendous amount of heat gets released. Now, when that first starts in the sun, starts a chain reaction, a shock wave will travel out into the solar system. That's actually really important. Okay. So now that it's a genuine star, the shock wave, okay, pushes the lighter gases away from the star's accretion disks further out, okay, leaving heavier elements like iron and nickel and so on closer in. That's important for later, okay, when we talk about the formation of planets. All right, so the mass of the star, so how much mass you have in the gas ball at the center, will determine what kind of star you get, whether you get a you know, one of the giant stars, or whether you get like a main sequence star. There are main sequence stars that are quite heavy, okay, that tend to live much shorter lifespans, okay, and then there's ours, which is sort of an average star. We see a lot of them, okay, yellow dwarfs, right, with a temperature of, you know, 6,000 degrees at the surface, but they have a lifespan of about 10 billion years, okay. All right, so most of the time, main sequence. Main sequence is most of the stars we see out there are on the main sequence, right? In that diagram that we talked about. Okay, so how do planets form? So let's talk about planets for a moment. So remember that the star is surrounded by an accretion disk. Well, before we get there, I have some pictures at the end. I'm going to explain all these pictures later. I just threw them in here. This image here is what a protostar looks like just after nuclear fusion starts in the core. So now it's a genuine star. As soon as you have nuclear reactions in the core, now you're a star. You're absolutely a star if you have hydrogen fusing in the core, okay? And things are going to get a lot brighter and a lot hotter in that solar system. And here you can see in this area here, like the star is in the middle in there, okay? But around the star, you see the accretion disk that I'm talking about. Now these jets will shoot out from the top and bottom when the star is first ignited. In other words, when fusion starts, at first stars will tend to eject material vertically, okay, away from themselves. Okay, remember it's a spinning ball of gas, and so that's what happens. And that can last for many millions of years, which is a very short period of time compared to the star's total lifespan. So here, this diagram here represents a protostar becoming a star. And here you can see right there, okay, that's the accretion disk. And maybe what I'll do is I'll color that line so you can see it a little better. That's the accretion disk right there. So that dust that settles around the star, that's going to become the planets. It's important you understand that this is already spinning. The whole thing is spinning around. Even the star is spinning around. Because that's what happens when gravity pulls things together. There tends to be a little bit of rotational action, okay, that occurs as material gets pulled in by gravity, and it just spins faster as it pulls in closer towards the sun, okay? All right, whoops. So now, where were we? Okay, so we're still talking about the formation of planets. Now that material, the dust and everything you see in the accretion disk, remember that the shock wave that gets sent out when the star gets ignited gets sort of blasted out, blasts out the lighter elements like the gases and stuff further away from the star, okay? And the heavier elements that are close tend to be a little bit closer in, okay? So that's why the first 4 planets in our solar system plus the asteroid belt, we think that's why they're rocky planets, okay? Because that shock wave pushed the gas back further, but the heavier elements were not pushed as far. That's why the inner planets are rocky, okay? So basically planets are formed when material in the accretion disk is pulled together by gravity, okay? So again, it's gravity that pulls things together, forms planets, moons, asteroids, etc., okay? So key point, larger masses will be attracted in the debris to form all the things that we see. Heavier elements closer to the sun form the rocky planets that we see. We think that would be quite common in solar systems that are like not our own, but other solar systems out there. And the lighter elements, which ultimately form the gas giants, they ended up being pushed out further into the outer solar system. Okay? All right, so that's how planets are formed, and that's how stars are formed. Okay, kind of interesting. Now, let's talk about the death of stars. Okay, when stars die, it's kind of a cool process. So let's talk about that for a second. Basically, stars die when they start running out of fuel. Now, the fuel for a star is the hydrogen at its core. Okay, so think about this for a second. Stars are fueled by nuclear fusion, and specifically when you fuse hydrogen into helium. Okay, that's what keeps them going. Now, there's a couple of things you need to understand. there are two forces that act on the star that are really important here. One is, picture this, like gravity tends to squeeze it together, so the star is very heavy. So you'd think it would collapse on itself and form something like very dense. But what's keeping that from happening is the nuclear reactions in the core. There's so much heat. Heat makes gas expand. So it's fighting against gravity, right? So our sun right now is middle-aged. There's gravity pulling it in, there's a nuclear fusion pushing it out, and those two forces are balanced right now. And so the star is stable and it keeps its shape, okay? Now that's what I was saying here. So number one, gravity holds the massive ball of gas together and creates enormous pressure at the core, okay? Now what this will tend to do is make the star collapse under its own weight, okay? But what prevents that from happening is nuclear fusion in the core and makes it try to expand. So that's the opposite of collapsing. And so these two forces are in balance with each other, and our star stays the same size. But it won't stay that way forever, okay? All right, when the star runs out of hydrogen, okay, it'll begin to collapse. Gravity's gonna start winning the war. But the thing is when the star collapses, now you've run out of hydrogen, but you've got helium there that the star is manufacturing over all these years, right? Over all these billions of years. That helium can fuse too at higher temperatures than 15 million degrees Celsius. So as the star starts to collapse, now the helium starts to fuse, okay? And when you fuse helium together to form heavier elements, what happens is that is even hotter than hydrogen fusion, okay? So now the core burns even hotter. And now gravity's going to start losing the war. So what happens is the star expands, okay? So what happens, the star begins to collapse. This forces heavier elements to fuse, releases more energy, and it makes the star expand. So actually, gravity first starts to win the war, okay? But then the fusion starts up again, this time with heavier elements than hydrogen, and then the star expands to this enormous thing we call a red giant. And at that time, that's the end of the Earth. So in other words, our sun will expand to something where Earth will basically be inside it. It's going to be so big, okay? Now, here's the thing. Our sun does not have a lot of mass compared to some other stars out there. So the sun, because it's now so big, it's going to start to lose its gravitational hold on its outer layers. And so what's going to happen is, because the star has an insufficient mass, it can't hold on to its outer layers, so they're going to float off into space, okay? I meant to say though there, okay? And the outer layers continue to expand, and you're going to expose the core of the sun will get exposed, okay? And the other outer layers just float off into space. Now at this point, we call these like formations, okay? Now the star is almost dead, okay? The white core that's at the center is very hot, but the nuclear reactions have run out. Like basically now you've run out of helium to fuse, okay, as well. And gravity cannot pull the star back together because the outer layers have drifted off too far away, okay? So now that forms what we call planetary nebula, which really are some of the most beautiful formations in space. Now I've got some pictures of planetary nebula here for you. I found these just by Googling it. The reason why they're called planetary nebula has nothing to do with the planets. What it does is, like, okay, when they first observed these in telescopes, way back when, they thought they were gas planets, okay, but they're not. They're actually dead stars, okay, and the way they look, some of them actually kind of look like planets, okay, even though they might not be perfectly spherical. But look at these pictures here. These are all planetary nebula, really quite amazing. In some of them, you can clearly see the core of the star, okay, being exposed, okay. Here you can see that white dwarf there in the center here. It's really clear right there, okay, in that picture. That's a really great picture of one there. Here you can see the core being exposed. And so that is a star like our sun. It's kind of like its corpse, right? Like it's shedding its outer layers, and this bright dot that shows up in the middle is the core, okay, where all the nuclear fusion has now ceased. But it's still a very hot ball of gas, and it glows white. okay, because it's so hot. So we call those white dwarfs. So when our sun dies, it's going to become something like this, okay? And that's got about another 5 billion years left, and it'll eventually become a white dwarf, okay? So planetary nebula, we saw what that is, and that they're very beautiful. It's really sort of an amazing thing to see out there in space. Eventually that white dwarf will cool off, okay? The temperature will drop, there's no more nuclear fusion, so it'll cool off because it's exposed to outer space, and it'll become what's called a brown or black dwarf. Now I've got a picture of that down here somewhere. That right there is a brown dwarf. It's basically kind of like Jupiter, if you want to think of it that way. The only difference is it's way more massive than Jupiter, since our sun's core would be way more massive than Jupiter. But just, you know, not enough to cause any fusion of the elements that are present in that ball of gas. But yeah, it might, in volume, it might only be about the size of the Earth. Okay, so smaller than Jupiter in volume, but larger than Jupiter in mass. So a really dense, okay, ball of gas. And that is a dead star right there. Ultimately what our star will look like in the end, okay? Now, bigger stars are different, okay? So if you have a star that is over 10 solar masses, okay, then what happens is, it starts out the same way. It runs out of hydrogen, okay, collapses. Helium starts to fuse, it becomes a red giant. That's all the same, okay? The difference is it won't lose hold of its atmosphere, okay? It won't lose hold of its outer layers because it's so heavy. So then what happens is gravity will actually cause the star to collapse even more, okay? So like it becomes a red giant at first, but it's so hot in the core of these heavy stars that you can get not only helium fusing, but even heavier elements, like for example, iron and so on, like what we see in the rocks all around us. Remember I told you that's where Earth comes from, a heavy star that died? Well, this is where iron comes from. Iron and nickel that make up all the rock and everything that you see around you, okay? So what happens is that gets tremendously hot, okay? So it becomes this red giant. Then when that runs out, it collapses in on itself. Like once you start fusing like iron, basically you're done with the fusion process after that. So once it's all done, you can't fuse past iron basically. So once that's done, the star collapses really quickly, and the collapse causes an explosion that we call a supernova. Now these are the biggest explosions in the universe. A supernova can be brighter than an entire galaxy. One star can be brighter than hundreds of millions of stars, just for an instant when it explodes, okay? So, I explained all that here in these paragraphs. So for stars that are bigger than 10 solar masses, they explode, okay? Then they do the supernova. And then that'll form a nebula, and maybe smaller stars can form from that, like our sun did, okay? Now, here's the deal. The core is still there. So after the supernova is done, the core is still there, but it's so heavy that gravity just compacts it into a really small space. Okay, now these are really strange objects. The exposed cores of supermassive stars are really strange, okay? You know, nuclear fusion stops, the core is really hot, it's spinning amazingly fast, okay, the dead core, because you've drawn all that material into a really small space, and it's like the figure skater dancing, right, or spinning, pulls her legs in and she starts spinning faster and faster. Well, the sun does that, like these stars will do that, and it's so extreme that they're spinning at an incredibly high rate. They tend to have very strong magnetic fields, okay, and they tend to emit radio waves, okay, in the form of pulses. And so we call the dead core of some of these massive stars neutron stars. They're not really stars anymore, but that's what they're called. But because they release pulses of radiation, we call them pulsars, okay? So, neutron stars or pulsars, the dead core of a supermassive star. Now I think I have a picture. This picture here is a neutron star. not really a star. There's no nuclear fusion going on. It's a dead star, okay? Or a pulsar. All right. So, neutron stars and pulsars. That's what those are. So that is the dead core of a star that has between 10 to 30 solar masses. This thing is city-sized, like maybe 20 kilometers across. It's super small. When you think about that, 20 kilometers, that's like not even as big as the city limits of Ottawa. But it might have as much mass in it as our sun has, okay? That is some of the densest material in the universe. So like what that means, put it in perspective, is you've got a star-sized mass packed into a city-sized space. It's incredibly dense. So that if you could imagine this, if you take a teaspoon of neutron star, it could be as heavy, has much mass in it, as the entire city of Ottawa, all the buildings, all the people, everything. Okay? And Thor's hammer is made from a neutron star, right? Maybe that's why no one can lift it. And of course, the key to Superman's Fortress of Solitude, I think I mentioned that to some of you in class. But here's the deal. I hate to burst your bubble. Let's say we were to take some neutron star and try to make a hammer out of it. Okay? Let's say it weighs the size of this, weighs as much as the city of Ottawa, or even more, maybe as much as the province of Ontario, all packed into a hammer. Well, the thing is that the only thing holding together that neutron star material is the gravity of the entire star. So if you were to take it away from the star, then it would expand and take up all the space it would normally take. So if it was as heavy as Ottawa, it would expand and take up all the space that Ottawa takes up, right? Become this huge rock or something, the size of the city of Ottawa. So that's the deal. Like unfortunately, you cannot remove material from the neutron star without it changing it, because the gravity, if such a thing were possible, it would just fly apart, right? Because now you've taken away the gravity that's holding it together. All right, so that's a neutron star. Now, if you have a really massive star, like supermassive stars, okay, bigger than 30 solar masses, the same thing happens as a neutron star, so it's the same process, so I'm not going to go over that again. It's the same process. The only difference this time is the exposed core is so dense, okay, maybe like incredibly compact, but so dense, like maybe with several, 5, 6, 7, 8, 9, 10 solar masses all packed into this really small place. And the gravity is so intense that not even light can escape it, okay? And those objects are called black holes. Now I can't show you a picture of a black hole because it just looks like a black object against the darkness of outer space is invisible, right? But there are some ways that maybe we could picture it here. This is actually a photograph of a black hole. We think that in the center is where the black hole is, and the bright halo around it we think is material that is accelerating towards the black hole. The light isn't close enough to the black hole so it can still escape, but anything that falls within this region here can't escape. Okay? We think there's a black hole there. All right, here's a picture of an artist's rendition of a black hole sucking in material from a nearby star. Okay? What's happening is there's an accretion disk forming around the black hole, and it's sucking in material, okay? And material accelerates down, into the black hole. Now the black hole is not actually a hole in anything. What it is an incredibly dense core of a dead star. So that's what a black hole is. Now in your book, they talk about a black hole that we think we've detected around the edge of the black hole around here. The material that's being sucked in can sometimes generate X-rays. Okay, and so we've detected these with what we call radio telescopes. You can't see X-rays with your eyes, but we have detected a source of X-rays out there in the heavens. And the one that we have detected, first one that we detected, they called Cygnus X. Okay, and we think that's a black hole. All right, so that's a lesson for now. That's actually lesson 12 and lesson 13. So please do those 2 lessons in the homework, and we'll talk to you tomorrow. All right, guys, have a good day. We'll talk to you.